Today we're taking a look at FRQ topic 4, which is data questions, data or table questions, where they give you a function or functions in a table. It's a very common topic on the AP exam. Okay. All right. You're given a table of data, usually a time and either an amount or a rate function. Okay. On a closed interval with usually an initial amount given to you. Okay. And you're asked to do a variety of things. Okay. Estimate a derivative. Use your closest 2 points to the value, to the time value that they give you, the independent variable that they give you. Use some sort of estimation technique for an integral. Okay, Riemann sum, midpoint sum, trapezoidal sum. Remember that the Riemann sum only gives you an approximate integral value. It does not take into account anything else that is asked for. Okay, know how to tell if that approximation is an over or an underestimate. Again, if you're asked to find an absolute min or max, you use the candidate's test. And oftentimes they want you to explain the meaning of something. Okay, you can use the NUT acronym for this. Remember that you want your noun of what it is that you're finding the meaning of, units on both time and your noun, and then your time. Okay. These are some of the things that you might have to give the meaning of. All right. Be sure to give the meaning in the context of the problem. They will tell you to, but be sure to do that. Don't say it's the average F. Say it's the average height of the tree, or whatever F means. Okay. All right. Let's see. Oh, they like, for these problems, MVT, IVT, they like that. Okay. There might also be an EVT question, which just says that there has to be a min or a max. Okay, and then oftentimes in part D, you'll be given some other function. Okay? Some with, some without. So be ready for anything. Look at it. First up, the problem from 2018. Okay. You see the scores. Pretty good score for KHS. Okay. Fairly good for a global average. All right, let's take a look. The height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters, t is measured in years. Selected values of h are given in the table. Okay. Use the data in the table to estimate h prime of 6. H prime of 6. And then, using correct units, give the meaning of h prime of 6. All right. Well, this is h. We want h prime. I know h prime is slope. We're going to use the average slope of the closest two time values. Okay. So in part A, I'm going to write h of 7 minus h of 5 over 7 minus 5 is equal to 11 minus 6 over 7 minus 5. Okay? That is my estimate for h prime of 6. Okay? By the way, you have to write that part. And you have to write that part. Okay? All the time I get students when I'm grading their test and they only write one or the other. And they'll say, oh, I didn't know I had to write the other one. Well, I'm telling you right now, you have to write both. Both of these are required. Don't just write the numbers because you have to say where the numbers came from. Don't just write that because that is not safe stop. I cannot go to my calculator and type in h at 7 like that. Okay, not safe stop. Okay, now for the meaning of it. I want the meaning of h prime of 6. Interpret the meaning of h prime of 6. Not the approximation I just found. I want the meaning of h prime of 6. So, at time 6 years. At 6 years. H is changing at a rate of. That's what I'm going to write, but I'm not going to say H. What is H? The height of the tree. Is changing at a rate of. H prime of 6 meters per year. Units of H, units of time. Units of H, units of time. That's it. Easy peasy. Part B. Explain why there must be at least one time between time 2 and 10 such that h prime of t is 2. H prime. The table has h. They want h prime. I know that this is an MVT problem. It's an MVT problem. I start with my basic conditions for MVT. H is both continuous and differentiable. Why can I say that? Since H is given to be, okay, what is H given to be? H is given to be twice differentiable. So that's what I write. H is given to be twice differentiable. So often, you guys, I'm grading a test, and I'll read something that says like H is given to be differentiable. No, it's not. It's not given to be differentiable. It's given to be twice differentiable. So don't tell me it's given to be one thing if it's not. Okay? Just say what it says. All right. Now for the meat part of this. I need to find an average rate of change that gives me 2. An average rate of change that gives me 2. So I want change in H over change in T to be 2. I want change in H over change in T to be 2. Okay? And I need to find out where that's true. Okay? I'm looking up here and I see it right away. 6 minus 2 is 4. 5 minus 3 is 2. 4 over 2 is 2. So I found it. So I'm just going to go write that down. H at 5 minus H at 3 over 5 minus 3 is 6 minus 2 over 5 minus 3, which is 2. I found it. Just like up here, you need all of this stuff. You need it, you guys. Alright, so write it all down. Now for my conclusion. Therefore, there must be. I'm going up here and I am rewriting this. It says explain why. This is what I'm going to write right here. There must be at least one time T for 2 to 10 such that H prime of T is 2. Okay? Part C. use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height. The average height of the tree. Well, the average h, I'm using my average value of a function formula, is 1 over 10 minus 2 integral 2 to 10 of h. That's the average formula, right? The trapezoidal sum will only give the integral part. I need to be sure to stick this part on. So I'm going to write 1 over 10 minus 2 times. Of course, you can make that a 1 over 8, but okay. Now I do the trapezoidal sum. So let's remind ourselves how we do a trapezoidal sum. I go to my first 2 time values. I average the heights times delta t. Average the heights times delta t. And then I go to my next set. Average those heights times delta t. Then I go to my next set. Average those heights times delta t. And then my last set. Average those heights times delta t. That's the trapezoidal sum. So, average my heights. 1.5 plus 2 over 2. That's the average of the first 2 heights times delta t, 3 minus 2, plus the next set. Average those heights. 2 plus 6 over 2 times delta t, 5 minus 3. Next set. Average those heights times delta t. Last set. Average those heights times delta t. Trapezoidal sum. Okay. Did they ask me to do anything else? Nope, no units, no nothing. Okay. Part D. Okay, the height of the tree in meters can also be modeled by G. So this is that other function that they're throwing at me. Okay? Where x is the diameter of the base of the tree in meters. So G is also the height, but it is in terms of x, the diameter of the base of the tree. When the tree is 50 meters tall, the diameter of the base is increasing at a rate of 0.03. So this is dx dt. It's the rate of x, yeah? Okay. According to the model, what is the rate of change of the height of the tree? So I want dh dt. Actually, I want dg dt. When the tree is 50 meters tall. When g is 50 meters. Okay? So I want dg dt. And there's g, so I'm just going to go and take the derivative of this one with respect to time, yeah? So g is equal to 100x over 1 plus x. I want dg dt, so I'm going to come in and take the derivative with respect to t. Little related rates problem here. So I get my dg dt, which is what I want, and now I need the derivative of this with respect to t. So first with the derivative with respect to x, then multiply by dx dt. So first derivative with respect to x. So quotient rule, 100, start up on top, take the derivative, 100 times the bottom left alone, minus the derivative of the bottom, which is just 1 times the top left alone, over the bottom left alone but squared, and then I'm multiplying that by dx dt, little chain rule there. Okay, implicit differentiation is a form of the chain rule. Okay, all right, now when g is 50, I want when g is 50, right? When g is 50, I know dx dt is going to be that 0.03. When g is 50, what is x? What is x when g is 50? Well, I can find out by putting 50 in place of g and solving for x. So I'm going to say 50 is equal to 100x over 1 plus x, and solve this for x. I'm going to multiply, actually I'm going to do ye old SAT trick and switch the 1 plus x and the 50. Actually, I'm multiplying both sides by 1 plus x and dividing both sides by 50. But it looks like those are switching. So I have 1 plus x is equal to 2x, so x is just 1. Well, that was handy. That worked out nicely. So I'm going to have dg dt is equal to, I'm putting 1 in place of x, so 100 times 2 minus 100 over 2 squared times 0.03. That looks a little awkward, so I think I'm going to do that. And that's it. I'm done with that problem. Okay, how was this problem scored? Let's take a look. 1.4 in part A, 1.4 the estimate. And there was a note that said you must have this and you must have that. There was a note in there. 1 point for the interpretation with units. So 2 points for part A. Part B, also 2 points. 1 point was for this step here, for the value of h of 5 minus h of 3 over 5 minus 3. And then 1 point for what they said, conclusion using MVT. Conclusion, using MVT, which means you have to have shown that MVT applies. Part C, also worth 2 points. 1 point for the trapezoidal sum. 1 point for the entire approximation. Part D, 3 points. 1 point for the quotient rule. 1 point for the implicit differentiation, the chain rule part. So did you have this dx dt there? And then 1 point for the answer. That's it. Okay. The next one I'd like to do with you is the problem from 2021. My students did not like this problem that year, even though they did fairly well on it. They came back talking about it. They didn't care for it. Okay. And I know it was just because of the situation that they were talking about. Okay. The density of bacteria, of a bacteria population, the density of a bacteria population in a petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f. Okay, let's think about that. We have this petri dish. Okay, and as the radius from the center increases, the density increases. So there's very few bacteria right around the middle, but as it grows, as it gets out here, there's a bunch out here. So the density is bigger at the outside, just to give it a little meaning, okay? All right, values of, okay, F is the density, values are given in the table, okay? It's increasing and it's differentiable. F is increasing and differentiable. Okay. Use the data in the table to estimate F prime at 2.25. So I go to the closest to R values, excuse me, and I'm using change in F over change in R. So part A, change in F over change in R. So F at 2.5 minus F at 2 over 2.5 minus 2, that is 10 minus 6 over 2.5 minus 2. Okay, so I estimated F prime of 2.25. Now I need to give the interpretation of that. Well, I know that it is the rate that F is changing exactly at 2.25. Okay? So I'm going to say that. At 2.25. Usually this is hours or days or something, but it's not hours or days here. It's centimeters. At 2.25 centimeters from the center of the dish, okay, the F, now I'm saying what F means. What is F? F is the density of the bacteria population. So the density of the bacteria population is changing at a rate of okay, F prime of 2.25, yeah, F prime of 2.25, now I need units. Units of F are right here, units of R are here, so it's this per centimeter, milligrams per square centimeter per centimeter. I'm not sure, but that was a hard one. I bet you a few of my students got all of that year. But anyway, I'm sure they tried. Okay, part B. The total mass in milligrams of the bacteria in the Petri dish is given by this integral expression. This is the total mass of the bacteria. Approximate this value using a Wright-Riemann sum with 4 subintervals. Approximate that value. So I need to start with the 2 pi that's out in front. I'm starting with that 2 pi that's out in front. Now I'm using a Wright-Riemann sum, but look in here, in this integral. It's not just a function, there's this additional r in there, right? So for the Wright-Riemann sum, I need to have both of those pieces be the right values. So this is I need the right r and the right f of r, and then I need delta r. So right r times right f of r times delta r. That's going to be each piece, each of the 4 pieces for that integral. So, for the first piece, for the first pair, write r, write f of r times delta r. So write r times f of r times delta r plus next pair. Write r, write f of r times change of r. 2 times 6 times 2 minus 1, change of an r, plus next pair. Write r, write f of r times change in r. 2.5 times 10 times 2.5 minus 2, change in r. One last one, last pair. Write r, write f of r times change in r. So 4 times 18 times 4 minus 2.5. Tough little problem. Part C. Okay. Is the approximation found in Part B an over or an underestimate of the total mass of bacteria in the Petri dish? Explain your reasoning. Okay. We're using a right-Riemann sum. Normally, it's just the one function inside. Since the function itself is increasing, a right-Riemann sum, the right side, using the right side of that rectangle, will be over it. What's going to change if I have the r in here? What is r doing? Well, in the table, r is also increasing, true? R is increasing. So I have increasing times increasing, which is also increasing, but I need to justify my answer here. So what is the more calculus-based reason for a function to be increasing? Well, this entire thing here is increasing if its derivative is positive. I need to take its derivative. So I'm taking the derivative with respect to r of r f of r, which is product rule, 1 times f of r plus r times f prime of r. Okay, f is positive, r is positive, f prime of r is positive since f is increasing. We're given that. That was given to us. So this is positive. And a right Riemann sum on an increasing function, I should say, therefore r f of r is increasing. A right Riemann sum on an increasing function yields an overestimate. Also a tough part to this problem. Okay, part D. The density of bacteria for 1 to 4 is modeled by the function g, by this function, for what value of k is g equal to the average value of g? Well, for the first time, we're going to be using the calculator that we were allowed in this problem. So I'm going to grab my calculator. I'm going to put in, clear out what's there. I'm going to put in G, and for Y1, carefully. Okay. And I want to know, when is this equal to the average value of this? So I'm going to come find the average value from 1 to 4. So average value 1 to 4 is 1 over 4 minus 1, integral 1 to 4 of g. And that average value is 9.8757. Okay. I'm going to store that in for A and then go to my y equals, because I want to know, when is this equal to that average value. Okay. In between 1 and 4, right? They asked me, k is between 1 and 4. So I need to change my y's because I need to include this. So I'm going to come up maybe to like 15. There's my R value. So I'm going to say what I'm doing. G of k is equal to 9.8757 at k equals 2.497. A rather tough little problem. How was this scored? Part A, that doesn't look like an A. Part A, 1 point for the estimate. Again, there was a note that said you have to have this and you have to have that. 1 point for your interpretation with units. Two points. Part B, 1 point for the right Riemann sum. One point for your approximation. Part C, 1 point. They awarded 1 point for the product rule on that integrand. So 1 point for the product rule and 1 point for your answer with explanation. Part D was worth 3 points. 1 point for the definite integral. One point for the average value. And 1 point for the k value, the answer. All right. So, data problems. Some were easier than others. I would say that this one was definitely harder than most data problems.